Lesson 6, Understanding Z-Scores. In this lesson, we're going to learn a new way how to interpret the normal probability distributions using the Z-scores. What is it? The table of areas under the normal curve is also known as the Z-table, and the Z-score is a measure of relative standing. This is what a Z-table looks like. So it contains the z-scores, corresponding z-scores of your raw data, and their corresponding areas under the normal curve. Later on, we're going to learn how to use this table in order for us to interpret the data under the normal curve. The areas under the normal curve are given in terms of z-values or scores. So either the z-score locates x within a sample or within a population. So these z-scores is another way of locating your values of x under the normal curve. What is the importance of the z-score? So raw scores may be composed of large values, but large values cannot be accommodated at the baseline of your normal curve. So they have to be transformed into scores for convenience without sacrificing meanings associated with the raw scores. Imagine having a data or a sample scores of a 200 item test. It would require a bigger curve or probability distribution curve. So for convenience, we can transform or we can create a z-score out of the raw scores given without actually sacrificing the meanings associated with these raw scores or values of x. Finding the z-value. So this is what we're going to do if we want to transform a raw score into a z-score or a z-value. So the formula for the z-score for population data is z is equal to x minus mean over standard deviation. So for population data, we use the Greek letter mu for the population mean and the Greek letter sigma for the population standard deviation. And we use the capital letter X to represent our given measurement or our raw scores. Now for the z-score for the sample data, we use the formula z is equal to x minus bar x over s, where x is the given measurement, bar x is your sample mean, and s is your sample standard deviation. So the z-score for population data and the z-score for sample data may have different symbols, but they're just actually the same. The formula in finding the z-score is just the proportion of x minus mean over its standard deviation. Let's have the following example to understand further. Given the mean is equal to 50 and the standard deviation equal to 4 of a population of reading scores, find the z-value that corresponds to a score x is equal to 58. For our solution, first we should write what is given in the problem. So we have our mean is equal to 50, our standard deviation is equal to 4, our x is equal to 58, and we're going to find the value of our z. So we use the formula z is equal to x minus mean is over standard deviation. Substitute the values, that would be z is equal to 58, that's our x, minus the mean is 50 over 4, which is the standard deviation. We simplify, 58 minus 50 is equal to 8 over 4. Simplify further, 8 divided by 4 is equal to 2. Hence, the z value that corresponds to the raw score 58 is 2. Our z is equal to 2. Let's have the second example. The heights of teachers in Santa Catalina National High School are normally distributed with a mean of 150 cm and standard deviation of 15 cm. The height of Sir Victor has a z-score of 3.25. What is the actual height of Sir Victor? So given here, our mean is equal to 150 cm, standard deviation equal to 15 cm, and our z is equal to 3.25, and we're going to find the value of x. Now remember, the x here represents the actual height of Sir Victor, and Sir Victor's z-score for his height is 3.25. So So we use the formula z is equal to x minus mean over standard deviation. Now simply substitute. Our z is 3.25 is equal to x is unknown, so we just write x minus our mean is 150 over the standard deviation, which is 15. So after this, to simplify further, we just need to cross multiply. So we need to multiply x minus 150 times 1 and 3.25 times 15. That would be x minus 150 times 1 is x minus 150, and 3.25 times 15 is equal to 48.75. So we need to combine like terms to find the value of our x. So we need to transpose negative 150 to the other side. So our next equation would be x is equal to 48.75 plus 150, and that is equivalent to 198.75 centimeter. So from here, we know that the actual height of Sir Victor at z squared 3.25 is 198.75 centimeter. Now the z values are matched with specific areas under the normal curve in a normal distribution table. Therefore, if we wish to find the percentage associated with x, we must find first its matched z value using the z formula. The z value leads to the area under the curve found in the normal curve table, which is a probability, and that probability gives the desired percentage for x. So here is our z table again, and this is where we can find the areas under the normal curve using the z values. Using also the areas in the corresponding z-scores, we can also identify the probability and the desired percentage for our variable x. Now here are the steps on how to find the area that corresponds to z value. Number 1. Draw or sketch on the normal curve and locate the given z value on the normal curve. Number 2. Shade the region of the curve according to the condition of z value, whether it is below, above, or between. Number 3. Use the table of the area under the normal curve to find the corresponding area. 4. Choose the appropriate operation based on step 2 and 3. So the step 4 is basically the rules in finding the area of your z-scores or raw scores. When the z value is to the left or any related terms, example below, less than, or lower than, just write the value we obtained in step 3. Another rule is when the z value is to the right or any related terms, above, greater than, or higher than, subtract 1 by the obtained value in step 3. And when the shaded region is in between the two z values, subtract the biggest by the smallest value obtained in step 3. And step 5, we label the shaded region. Let's have our first example. Find the area that corresponds below z is equal to negative 1.35. For our solution, step 1, we draw or we sketch the normal curve. For step 2, we locate the z value negative 1.35. So it's found, we can find it right over here. So we'll just mark it with a line. That is our negative 1.35. Z is equal to negative 1.35. Okay, for the next step, we know that the area that we're going to find is the one below z is equal to negative 1.35. So we actually shade the area below negative 1.35. So if it is below, we shade the left corner of our curve from the line. So there is the area that we're going to find in the distribution table or in the z table. So in finding the corresponding area of our z-score, we know that the z-score is at negative 1.35. On the left corner of our z table here, we can find here the negative 1.3. And since the area that we're going to find is for the z negative 1.35, we also need an additional 0.05 because negative 1.3 plus 0.05 is equivalent to negative 1.35. So there's our z is equal to negative 1.35. To actually find its area, you just find where these two values or these two z-scores here cross. Okay, the intersection of the lines that we're going to make is going to be the area of our z is equal to negative 1.35, and it is right over here. Hence, the area at z equals negative 1.35 is 0.0885 according to the z table. Now, remember that we need to find the total area below negative 1.35. So, the first rule for step 4 is applicable. When the z value is to the left or any related terms, example below or less than, just keep the area. Hence, our area is already 0.0885. That will be our answer. That would be the area that corresponds to the region below z is equal to negative 1.35. Now, if you want to change it, and if you are asked what percentage of the whole data are the datas below z is equal to negative 1.35, you just simply multiply our area by 100%, and that is equivalent to 8.85%. So to make inference and to interpret it, 8.85% of the data is below z is equal to negative 1.35. Now let's have the second example. Find the area to the right of z is equal to negative 1.35. For the solution, for step 1, we draw or sketch the normal curve. So here is our normal curve. Next, we locate negative 1.35. It's the same with example number 1. So our negative 1.35 is right over there. Now it says here, find the area to the right of negative 1.35. So we actually shade the region at the right side of negative 1.35. Now we're going to find the area that covers this shaded region or this shaded part of our normal curve. So a closer look at the z table, the negative 1.35, we can find negative 1.3 at the left side and the 0.05 at the right side. And the area is equivalent to 0.0885. 0.0885. Now, that is the area that corresponds to negative 1.35. Now, since it says to the right, the rule number 2 in step 4 is applicable. When the z value is to the right or any related terms, e.g. above, greater than, subtract 1 by the obtained value in step 3. So, from our area, we actually subtract it from 1. So, this area is equal to 1 minus 0.0885. So again, if the shaded region is to the right of your z value, you just subtract it from 1. And the answer is 0.9115. So, or hence, the area to the right of negative 1.35 is 0.9115. If we want to convert it to percent, just simply multiply it by 100%, and that will be equal to 91.15%. Hence, we can say that 91.15% of the data lies to the right of negative 1.35 at z negative 1.35. Now, let's have the third example. Find the area between z is equal to negative 1.30 and z is equal to 2. For the solution, let's first draw the normal curve. This is our normal curve, and we will locate our z values at z is equal to negative 1.30 and z is equal to 2. So we just label it with a line. There is our z negative 1.30 and z is equal to 2. And since our problem states asks us to find the area between z equals negative 1.30 and z is equal to 2, we shade the region between these two z values, and that is the area that we're going to find. So first, we need to find the area associated with z is equal to negative 1.30. So looking at the z table, the area at z is equal to negative 1.30 is right over there. So we have the negative 1.3, and since it's a 30, we just cross it with a 0.00 above. So where they intersect is at 0.0968. Now, let's find the area at z is equal to 2. Looking at the z table, the area at z is equal to 2. So at the left, we can write it. We can see the 2.0, and with the 0.00, that is z is equal to 2, and the area is equivalent to 0.9772. Now, to find the area of the shaded region, let's go back to the rules. In step 4, the third rule states, when the shaded region is in between of the two z value, subtract the biggest by the smallest value obtained in step 3. So we will just have to subtract. So our area then within the shaded region is 0.9772 minus 0.0968. That is equivalent to 0.8804. So the area of the shaded region is 0.8804. If we want to convert it into percent, we just have to multiply it by 100%. So 0.8804 times 100, that is 88.04%. So we can now say that 88.04% of the data is in between the z-score negative 1.30 and z is equal to 2. That's it for understanding z-scores, finding the z-value given the standard deviation, the mean, and the row scores, and finding the corresponding area of the z-score under the normal curve using the z-table. I hope you learned something from this lesson. And don't forget to have a statistic amazing day.